So now that you've had some time to kind of figure out what NetLogo is all about, we've had some fun out in the courtyard playing around with games, right, and acting out as agents, right? We're going to take a step back and we're going to talk about how to build ABM from the ground up, right? So we built these kind of like simple toy models, but those really weren't models that necessarily you're going to use for a particular scientific experiment necessarily. The simple wealth one maybe you could use, but so how would you design a model from the ground up for a scientific publication or a scientific paper, right? So the first thing I want you to understand, right, is that ABM is quintessentially what we call a generative science, right? We are generating data, right, that we're then going to use to kind of test our hypotheses, right? Our model is our hypothesis. We generate data from that model, and then we compare that model's data to real-world data and determine whether or not our hypothesis is true a lot of times, right? And, Richard Feynman had this great quote. This was what was on his blackboard around the time of his death. And Richard Feynman's famous physicist, for those of you who don't know, right? What I cannot create, I do not understand. Know how to solve every problem that has been solved, right? So what he was saying, basically, is that if you don't know how to create the phenomenon you're seeing, you don't really understand it, right? Just having, Josh Epstein said this a little bit different way. He said, if you can't grow it, you didn't show it, was his famous quote, right? And so what he was arguing was, even if you identify a pattern of behavior in a system, if you can't talk about how that pattern of behavior came to be, then it's not necessarily, you don't really understand how that pattern of behavior exists, right? And agent-based modeling is fundamentally about figuring out how to create those patterns of behaviors. How do they come about, right? So there are three major steps to designing any agent-based model. Design the model, right? Like kind of conceptually design the model. Build the model, implement it, and analyze the results, right? And we're going to talk about each of those today a little bit in turn. So there are, it's funny, when me and my co-author, Uri Walensky, sat down to write the textbook, we kind of had a little disagreement about how to actually think about designing a model. Because in my mind, the best way to do the model is what I call phenomena-based modeling. You observe a phenomenon in the real world, you make some hypotheses about what might give rise to that phenomenon, and you build a model to show whether or not those hypotheses are true. That's the way I like to think about modeling. But Uri is kind of like, he likes to play, right? And so he likes to think about it from the bottom up. He likes to say, I see people do these things in the world. If everyone does those things, what happens as a result of that, right? And so that's what he calls exploratory modeling. You start with a basic set of mechanisms and then explore what those mechanisms can possibly generate, right? So there are two different approaches, right? And it's, I think all of agent-based modeling is really bottom-up, but you could think of this as a top-down versus bottom-up approach to designing your model, right? And my approach tends to be more top-down, where Uri's approach tends to be more bottom-up, right? So that's basically what I just said, right? In the top-down approach, we're going to start with the components and the design, and then put them together. Whereas from the bottom up, we're going to kind of co-evolve the conceptual model and the code simultaneously, right? So we have these mechanisms we know exist in the world. We're going to kind of play around with them, see what kinds of patterns of behavior they generate, then kind of go back and revise our conceptual model and revise them. Whereas in the top-down approach, we start with more of a design and then build the model to match our design, right? It's rare that either Uri or I build models with just one of these methods, right? Both of us tend to go back and forth. Like I start with a top-down design, I start building my model, and halfway through I'm like, oh, well that mechanism kind of does something different than I thought it was going to. I need to reevaluate my conceptual model, right? And so the whole point of this is just to say that there's a constant iteration, a constant cycle between developing your model and developing your conceptual model and developing your model and developing your conceptual model, right? So Ernie and I decided to we wanted to come up with one principle that we thought was the most important principle that you could possibly think about. And this helps us guide every decision we make when building an agent-based model. And that principle is start simple and build toward the question you want to answer, right? So if you have a research question in your mind, right, or a research phenomenon in your mind that you want to explore, then you want to start with the simplest possible model that will help you answer that question. And only add complexity to your model as you need it to answer the question, right? So you don't need to add complexity right away, right? You only add complexity as it's necessary, right? And this is, I mentioned briefly that Albert Einstein had a quote that was often misattributed, right? And this is actually the full version of the quote. The supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience, right? So in other words, what he's saying there is make your models as simple as possible to account for the phenomenon you see, right? That's what he's saying, right? And William Occam's razor, do not multiply entities unnecessarily, right? Given two versions of a model that explain the same thing, the simpler one is probably the correct one, right? Is essentially what Occam's razor says, right? And then Robert Axelrod, famous agent-based modeler and political scientist, said it in even more direct language, keep it simple, stupid. He called it the KISS principle of agent-based modeling, right? So just keep your model as simple as possible. Why should you keep your model simple? Well, first of all, keeping your model simple helps confirm that all the mechanisms are necessary, right? If you have the minimal amount of model that needs to generate the empirical patterns that you're seeing in the real world, and you remove any one of those mechanisms, the model should no longer generate those patterns you see in the real world, right? Which seems to imply that all those mechanisms are necessary. It's easier to understand for both you and someone else a model that is simpler, right? If it has less parts to it, it's easier to understand. It facilitates two important concepts that we'll talk about on Monday, which is verification and validation, right? Verification is the idea that your implemented model, your actual code, matches your conceptual model, the model you have in your mind, right? Validation is that the model that you implemented actually models real data that you see in the real world, right? It allows you to more easily examine the components, right? If your model is simple, then a particular component of that model is going to be there's going to be less complication necessary to use that component, right? So it allows you to pull that component out and replace it with another component a lot easier. Whereas if your model becomes more complex, replacing components of the model can become more difficult. Build toward a question, the second part, right? So this is where that George Box quote that I mentioned yesterday also comes up, right? All models are wrong, but some models are useful, right? Don't put things into the model just because someone tells you should put it into the model, right? I don't know how many times I've worked with subject matter experts when we're trying to build agent-based models of complex phenomenon, and they're like, oh, but we all know that this is an important aspect, right? And they have me put something in there, but if it doesn't really affect the behavior of the model, why would you do it, right? Or if it doesn't really present any interesting insights. To give you an example, I was building a model of residential location choice, so where people decide to live, right? And I asked one of our subject matter experts what the research and literature said about that, and they came back with a decision tree that had like 30 branches on it, right, of the different things people would consider when making a choice, right? And I was looking at the decision tree, and I was thinking about how I would implement it and how I'd work with it, and I realized that all but about 3 of the branches really kind of resulted in random decisions, right? And so there were kind of like, I could replace large chunks of this tree with just flipping coins, right? And it would result in almost the same pattern of behavior, right? And so I did it, and I showed that the results were about the same, right? That there were no real difference to them. And I thought that was a great example of how, I put in the complication I needed, but it wasn't any more complication than was absolutely necessary. And it built toward the question that we wanted to answer, which was, what would be the pattern development that we see in these landscapes? Throughout this unit, we're going to be building an agent-based model from the ground up. That's what we're going to do in the tutorial this afternoon, right? In this case, we're going to be building a model of new information diffusion through a population. And this is an area that's very important for me. I'm very interested in diffusion of information. I think it's a fundamentally important question in today's world. How do people find things out? What do they do with that information once they have it? And how do they pass it on to others? So I'm going to use this as a great example. And I think that this is a model that works very well if you're interested in sociology, if you're interested in psychology, if you're interested in marketing, if you're interested in economics. How do people decide what products, what stocks to buy, right? This is an important question to know, right? And so I think it's a big question. So the basic question we're going to try and build toward in our model that we're going to build is, how does novel information diffuse through a population over time, right? And this afternoon, I'm going to spend some time with you talking about how to build that model. But today, we're going to talk about this morning, we're going to talk about how to design that model instead, right? So let me give you an example. This is it's a classic graph from, I think this is from Everett Rogers' book on diffusion of information, right? Diffusion of innovations. No, actually, it's not from Everett Rogers, but it has some of the Rogers graphs in it. So on the top, we have a graph that kind of represents the standard pattern of technology adoption of a new product, right? So early on, we have what we call innovators. These are people who try out any new product that comes along, essentially, right, and want to see how well it does. And they get in right on the ground floor. They're a very small percentage of the population. Those innovators convince some larger group of early adopters to adopt, right? And then we have the early majority who adopt, the late majority, and then what we call the laggards at the end, right? And almost every single population follows, every single new technology product follows this kind of a pattern of behavior, right, of adoption, right? And if you look at, this is looking at it, the way this is graphed right now, it's showing the adoption in terms of individual adoptions over time, right? But if you look at it cumulatively, it results in an S-curve, right? If you look at the fraction of the population that's adopted, that's kind of standard. Another way to think of this is the Bass model. And the Bass model is a model proposed by Frank Bass, an earlier important marketing scholar, in 1969. And the way Bass models it is that the adoption of any piece of innovation or information can be contributed to by two factors. What he calls the coefficient of innovation and the coefficient of imitation, right? There's a small fraction of possibility that I will adopt something just because I think it's cool, right? Because I saw a really cool ad, I was exposed to some cool marketing, right? I read a cool article in Wired magazine about it, whatever, right? There was some reason why I just went out and decided to buy, an Amazon Alexa, right, or whatever. There's a much larger fraction of innovation adoption that happens because of imitation. We see our friends adopting it, or we talk to our friends who are adopting it, right? We talk to our friends, and they're all watching Game of Thrones, so we go home and watch Game of Thrones, right? And that's the coefficient of imitation, right? And so he has a model where when you put these two together, you basically can reproduce numerically this same pattern of adoption that's very similar to Rogers' adoption models. So here's the Bass model. I said that there are very few equations in this class. This is one of them, right? So here's the Bass model written as a hazard rate model. So in the Bass model, the rate of adoption of individuals any time period t is equal to p plus q times f of t, where f of t is the cumulative fraction of adopters already. So q is the coefficient of imitation, and p is the coefficient of innovation. You can also think of p as external forces, right? Forces outside the social network. Q is internal forces, forces inside the social network. You could think of P as the tendency to adopt to do independent of social contagion, and Q is the tendency of adopt dependent on social contagion, right? It's a very simple model. There's also one other parameter that has to go into this, which is the market size. That's how we can calculate the fraction of adopters, right? So you can think of an agent-based version of this fairly simply, right? We're going to set up a population of M agents, and at each time step, those agents will determine if they will innovate on the basis of P of A, innovation, so their own personal innovation probability, and Q of A, imitation on the basis of other adopters, where Q of A is multiplied times N of T divided by M, the number of adopters at time T divided by M. Right? And then we'll simply observe the number of adopters. Right? So I'm designing this model. Right? So how am I designing this model? Right? I came up with my big question. Right? I then went and did a little research into the theories that had explored that question before. I then thought about how would I take that model and move it towards an agent-based model, right? Now, why am I moving it towards an agent-based model, right? Well, I'm moving it towards an agent-based model because it seems to feature many of the hallmarks that we talked about yesterday, right? Does it have a medium number of agents? Well, if Bass is right, and that there are a small group of adopters who adopt early on and they influence the rest of the population, it seems like there's a medium number of agents that can affect a large amount of the population. Is there time in the model? Yes, there's definitely time in the model, right? We're looking at adoption rates over time. Are there complex but local interactions, right? Well, in the original Bass model, maybe not so much, right? Because basically I'm just observing all the population. But what if we don't observe all the population? What if we only observe our local neighborhood, right? Well, if that's the case, then yes, right? There are some complex but local interactions. Are there rich environments? Well, in the original Bass model, probably not, right? It was what we call sometimes a pan-mictic model, an all-mixing model, where everyone can see everyone else. That's not very complex. But if I move towards a social media space or a social network space, right, then the network becomes rich, right? Because now every person in that space identifies a separate, unique location where they're sitting on the population, right? Heterogeneity. Right? Is there heterogeneity in the model? Well, in the original Bass model, no. Right? Everyone had the same P's and the same Q's. Right? So there was basically homogeneous individuals. The only difference between people was whether or not they'd adopted the innovation. Right? But you'll notice I subscripted P and Q with an A. Right? A being the particular agent who is adopting. So I can give heterogeneous values in this model, right? I can give the ability for agents to have different levels of innovation, different levels of imitation, right? Maybe resulting in more of these classic standards of innovators, early adopters, early majority, late majority, laggards, right? So I can put that straight into the model, right? So that will allow me heterogeneity. Adaptive model, it's not an adaptive model right now, but we don't need that. That's okay, right? Like we could think about that if we wanted to in the future. But there's agent-based models don't have to be adaptive. It's just if the systems are adaptive, it makes them more likely to be necessary to use an agent-based model. So there are 7 design questions you should face when designing your model. What part of your phenomenon would you like to build a model of? This is sometimes called the scope or the question, right? What are the principal types of agents involved in this phenomenon, right? What properties do these agents have, right? We already saw, for instance, in the simple wealth model, the agents had wealth, right? What actions or behaviors can these agents take by agent types? How do these agents interact with each other or with the environment? These are behaviors, right? What things can they do, right? In what kind of environment do these agents operate? Are there environmental agents? Are there agents, is the environment itself an agent within the model, right? If you had to define the phenomenon as the discrete time steps, what would happen during any one time step? And what do you hope to observe from this model? Once you've answered these 7 questions, you essentially have a conceptual model, right? So as you go away, in this class, with just 3 days, we're not going to have enough time to really have you build your own models, right, from the ground, like on a phenomenon of your own interest. We're going to do most of it guided, right? But as you go forward, if you want to build an agent-based model of your own phenomenon, these would be the 7 questions you would ask yourself first, right? And you can think about them as scope, agents, properties, behaviors, environment, time, inputs, outputs, right? And once you have those 7 questions answered, right, you have started to think about what your model is, right? These questions are also not just important for you as you're designing an agent-based model, they're important for the scientific publication. We recommend, actually, in a paper we wrote called Agent-Based Modeling and Marketing Guidelines for Rigor, we recommend that everyone who publishes a paper basically explains the answer to these 7 questions when they're describing their model, right? And by explaining the answer to these 7 questions, you've essentially described the conceptual model to me, right? Probably, if you do it well, at a level that's detailed enough for reproducibility. Does that make sense to everybody? Any questions about that? Any questions that you think should be added? What? Yeah, so this is definitely a top-down approach. I should also say, right, even if you start with the bottom-up approach, right, and you're playing around with the mechanisms, at some point you need to answer these questions. Because when you go to publish a paper, you can't just say, I threw a bunch of agents together and played around with them until they did something interesting, right? That's not the way science is done, unfortunately. It should be, right? Honestly, it should be. I think it would be much better if all of our scientific papers were like real narrative descriptions of how we did the science, right? Instead of actually formal descriptions like they are. But given the fact that the world is the way it is, right, we need to write formal descriptions of our models in order to get them published. And so we do eventually need to answer these 7 questions regardless. Okay. Great question. Any other questions? Okay. So let's talk about the diffusion model, right? So scoping question. Before you design anything, make sure it makes sense to model your question as an ABM. And that was kind of what I just went through when I talked through all the different, the 6 hallmarks of agent-based modeling, right? So we've already decided this is an appropriate question to use ABMs to understand, right? Now we're going to refine the research question in light of these advantages, right? So sometimes, as you're thinking about your research question, if you've decided to use an ABM to explore it, you might think about ways that can differentiate the ABM from non-ABM approaches, right? And I'm a big fan, like I mentioned yesterday, if you can answer the question another way, start there, right? So start with the BAS model. We already have the BAS model. We know what the patterns are. We can use that to understand what's going on, right? But now, if we're going to build an ABM, we should build an ABM that reproduces the BAS model, for sure. But then where will we go with it after that, right? And so one thing we could do would be to add network heterogeneity, right? Add the fact that people are in different places in the network. Maybe add the fact that different individuals have different innovation and adoption rates, right? Imitation rates. Add local but complex information, right? Maybe we can have some individuals have different sources of information from others, right? So maybe some people pay attention to tech blogs and some people pay attention to CNN, right? And so maybe they get different information as a result, right? So if that's the case, we can think about adding these different aspects. And so we could refine our original question. How does novel information diffuse through a population embedded in a social network based on both broadcast and local information drivers, right? So we've added this idea of a social network, right? And we've added this idea that there are 2 effects, the local information that we get from our social network and the global information, right, that we get from the broadcast signals. Agents. So what are the agents in this model, right? You often, when you're answering this question, you want to think about this from the question of what is the granularity or the level of the agent, right? And a lot of times you want to make this related to the temporal scale of interest, right? If I'm interested in how people over the course of a day decide to adopt an innovation or not, that might be very different than if I'm interested in how people decide to adopt innovation over the course of decades, right? if I'm interested in the spread of disease through a population, if I'm looking at an hour, I'm going to look at a different level of spread than if I'm looking at a year, right? So it's often helpful to think about it through that respect. But in most cases, for a lot of social systems that you're thinking about, inevitably the level of agent you want to look at is the individual, right? Maybe a group or an organization, right? Maybe a corporation or a government, right? But a lot of times it's at the individual level, right? But you could do it, just to point out, it could be at other levels, right? You could think about cellular level processes, right? You could think about organizational level. You could think about the individual human level. There's also something we sometimes call proto-agents that we put into these systems about this time, and it's worth thinking about that. What a proto-agent is an agent that hasn't yet become an agent, right? It's an agent we're going to build to our model because eventually we want to do something cool with it, but we want to first do the simplest possible thing with it, and so we're going to put it in there right now, and maybe later we'll give it its own properties and behaviors, but right now it's kind of fixed, right? So a good example of that in our model might be broadcast media, right? Maybe we want broadcast media to have its own news cycle and things like that, and so sometimes it pumps out more information, and sometimes it pumps out less. But right now, we just want it to have an effect on everyone. So we could think of it as just a proto-agent that's connected to all the other agents in our model and just gives them all the same basic signal right now. But maybe over time, we add a time-varying element or something else to it, right? So in the diffusion example, we definitely want human individuals. We maybe want two types of human individuals, right? We can talk about this, but there's a lot of literature that talks about the difference between influentials and imitators. And I mentioned this briefly yesterday, but an influential, there's the influential hypothesis in information diffusion says that there's a small fraction of people who actually care about product adoption, right? They actually care about what products they purchase. And usually it's particular to a typical area. And you guys might think about this in your own lives. Is there someone you know who, if you were going to buy a new computer, you would go and ask for advice, right? Is there someone you know who you're going to buy, if you were going to buy a new moped, right, you would go and ask for advice? Is there someone you know who you're going to buy a new phone, you would go and ask for advice, right? Those are the influentials, right? Those are the people who know more about this. And the hypothesis is often that there's like 1 to 10% of the population are influentials, and all the rest are essentially just imitators who buy whatever. So we might want to model the influentials and imitators differently, but we'll leave that for now, right? We might want to put network connections in the model, obviously, right? We're going to have links in the model, and we might have media as its own agent in the model. So that's potential. Now, right now, I'm just doing the design of the model. Eventually, when I go to publish the model, I'm only going to describe whatever agents I actually put in the model, right? But right now, at the beginning, when I'm designing the model, I kind of want to brainstorm and write down all the possible things, right? Properties. So what properties do these agents have, right? What properties do they possess? In the diffusion case, there's really only 3 properties I can think of. They have the property that they have the information or not, right? They know the information or not, right? They have the property of how affected they are by social influence, by their neighbors, and they have the property of how affected they are by the broadcast media or advertising, right? Those are the only 3 things I can think of. You could think about maybe making these more specific. It could be that users not only have an effective social influence, but have an authority on a particular topic. So maybe on some particular topic, my friends are more likely to listen to me than on other topics, right? And you can make this more complex, but for now, let's leave it at this, right? That there's these 3 basic properties. Links in media might not have separate properties right now, but they might in the future, right? And those are essentially the basic properties that our agents have. Any other thoughts or any other ideas as to properties that you could include in this model? If you don't, that's fine. Just kind of curious. Okay. So behaviors. Behaviors are what can the agents actually do. In the information diffusion case, it's simple. They either adopt the new information or they don't, right? They either decide that they want to believe that information, or they decide they don't want to believe that information, right? And you could think about this, if you're modeling this off of real data, let's say you are modeling off of Twitter adoption, right? Then the decision to adopt the information might be that you retweet or post the content, right? So you could think of this as an actual action and not just a mental decision of the person, right? Yeah. There could be, yeah. We haven't decided for sure. Well, there might not be a different behavior, but what is more likely to happen is maybe the effect of social influence and the effect of broadcast media is different, depending upon who those people are, right? So one way to think of it is that if I'm talking to an influential, they're going to have a greater social influence effect on me than if I'm talking to an imitator, right? And if an influential is talking to an imitator, there might be no effect of social influence on them. They might only be affected by broadcast media or other influentials, right? So the behaviors might be the same, right? Do I adopt or not? But the properties that decide those behaviors might be different, right? And that might, in the end, it might be that we wind up with different roles, right? But really, the only action either one can take is, do I adopt the information or not? Right? So what is the environment that the agents operate in, right? And yeah. So yeah, in other models, yes, right? In this model right now, we're just going to represent that they adopt or not. But you could think about, the Twitter example is a great example, right? Let's say that I'm a user on Twitter. I'm monitoring all my information feeds, and some of my users express things differently than other users, right? And I decide to retweet that information, right? That would be one way of adopting that information. But I might decide, instead of retweeting that information, I'm going to comment on a post that one of my friends made. So I'm going to reply to their tweet. So that would be a different adoption action, right? We're going to simplify all that for now, and we're just going to say you adopt, and it's the same no matter what. But yeah, you could imagine that being different. Yeah. Yes, in most cases. Yeah, it's a great question. So when I say that there's no global information affecting agents in agent-based modeling, what I mean by that is that an individual agent can't know the global state of the system, right, very easily. But there may be common information, right, that's not global information necessarily, that all the agents have access to, right? So it may very well be that all of us can watch CNN, right, and get the same information from CNN, right? Or if you're in the south of the US, Fox News, right? And so we can watch those channels and get our information from there, and we can all get that information simultaneously, right? But that's different than global information, where I immediately know what my agent, what another agent 20 links away from me did, right? Do you understand the difference there, right? So it is a global signal, but it's not a global signal that is unreasonable for all the agents in the system to know, right? And so I tend to think of them actually as in this different space of global being global state of the system, and common being some common resource that all the agents have access to, right? And it's okay to have common resources in agent-based models. It's less okay to have global resources in agent-based models. And somewhat it's a matter of wording. It's really not a big deal, right? But the real bright line, I think, is it realistic that a human moving about the real world in this context would have access to that piece of information? If it is, then it's okay if everyone has access to it. But a lot of times, and a lot of models out there provide the agent with information that they wouldn't have access to otherwise, right? Like a classic example is that, I go in to a market and I go to haggle about a carpet, right? Under traditional economics, I would immediately know what the real value of that carpet is by being haggled about by hundreds of other people or thousands of other people throughout the world, right? But in reality, there's no way I have access to that information, right? I just know my past experiences with buying carpets, and I can use that information to inform this decision. But I don't really have any other access to information, right? I guess if maybe there was a news channel that published the price of carpets on a regular basis, right, then I could have access to that information as well. But that doesn't exist. Does that make sense, kind of the difference there? It's a little bit tricky, right? Because we say no global information, and then occasionally we put these kind of global information signals in. But they're ones we'd expect to exist. Yeah? Yeah. So I think I understand your question. So let me see if I get it right. Your first question is, how do we, most of the model is dependent upon this local information spread, but we also have a broadcast signal. How do we relate those two to each other, right? And your second question, if I get it, sorry, I forget what the second question now is. Oh, yeah. So every agent has its own effects, right? How do we quantify the overall effects of one of those over another? Great questions. So for the first question, essentially one way we could do this, I'm not saying it's the way we will do it, but one way we could do it is we could make a new agent type, which is a media agent, and have that media agent have network connections to every single other agent. And so therefore, it just becomes kind of a local connection, but it's a global network type, right? So that's one way to do it. We could also just do it by just having a property that says that there is this kind of global effect in the background of the world, right? So that's another way we can do it. And we'll explore how we do that this afternoon, right? Yeah, exactly right. So then we can just give a number quantifying that effect, right? Now, if everyone has different levels of effects, how do we quantify the overall effect? That's a good question. One way we can do it is, even if they have different levels, we can say that they're within a certain bounds. So we can say that the local network effect is from, quantified from like 20 to 30%. And actually, usually it's higher. It's like 50 to 70%, right? So even though it's different, it's within that range, right? And the global network effect is 30 to 50%. And so even though it's different, it's in that range, right? And so therefore, we can kind of control those a little bit. And, we'll get to the heterogeneity aspect of this is not terribly important right now. We'll get to that eventually, basically. But does that make sense kind of at a high level? That even though they're different values, we can control the values that they're choosing from. And so that allows us to run experiments where we increase mass media effect, decrease social influence effect. The standard way we would do this is have say that the effect of mass media is drawn from a distribution of some sort, right? And we can characterize the mean of that effect, and then we can compare the mean of that effect to the mean of the local network effect and use that to kind of characterize it too. Does that help explain? Yeah, okay, cool. Is there another question up there? Okay. So what do the agents do? Well, they decide to adopt information. That's what we talked about. That's really the only action that they take in the system. My headphone is coming off real quick, so fix that. Okay. What is the environment that the agents act in? Well, they act in essentially the social network, right? But there's also this background media that they act in as well, right? And that could be, we could represent that as part of the network, or we could represent that as just a force in the world, right? That kind of affects everybody. And either way would probably be appropriate. So what happens in a single time step of the model? Well, each agent needs to decide whether or not they're going to adopt the information. They then update their internal state as to whether or not they're going to adopt the information. And then they essentially transmit that information in the next time step to the other people, right? So at the beginning of this time step, each agent observes their neighbors, right? Decides looks at what their neighbors have done, then decides whether or not to adopt. They then update their own internal state, and at the next time step, the agents observe their neighbors again. So this is what we would call synchronous updating, because the agents don't take any action until they've observed all the actions that their neighbors have taken, right? Does that make sense, right? So I look at my neighbors, I see which of them have adopted the information, I make a decision to adopt or not, but I don't change my state until all my neighbors have had a chance to observe me, right? And then after all my neighbors have a chance to observe me, I change my state, and then the next time step, I do it. And then, often in almost every model, at the end of every time step, we're going to calculate some sort of set of statistics. Right? And this model is going to be the fraction of adopters, right? But it could be other things. So what are the inputs and outputs to this particular system, right? So what are we interested in modifying? That's the parameters of the system. We're interested in modifying the network structure, right? We want to know how different network structures maybe affect different diffusion patterns. We want to look at the effect of social influence, how important the social influence is on individuals' decision to adopt, and the effect of mass media. How important is mass media on influencing users to adopt, right? And then finally, maybe the number of agents plays a role too as well. So we could put that in as a parameter also. And then outputs, we're really only interested in one output. How many people adopt over time, right? Now, if we split this up into influentials and imitators, maybe we want to look at how many influentials adopt and how many imitators adopt over time. But generally, we just want to look at how many people adopt over time. All that makes sense? Yeah, so in this case, we're going to assume that information is monotonic, right? That it's just one unit. So there are no levels, right? It's just whether or not you've adopted the information at all. But yes, you could think of a more complex model where, say, there's knowledge about climate change, right? And I could have a little bit of knowledge, or I could have a lot of knowledge about climate change, right? In that case, you could think about having different levels of the amount of information that each member of the population can get. And our model is going to be very simple. It's going to be something like, it's going to be something like, I'm going to go see Avengers Endgame, right? Like that could be the information that's adopted, right? Something that's a very monotonic type of piece of information. Or I believe we need to decrease carbon dioxide emissions, right? Or something like that, right? So it's not a complex object. This is a very simple object that we're adopting. Yep. Yeah, well, I think that's a very good question. So the question is, essentially, if we see a system in which 10% of the population has adopted 90% of the information versus 90% of the population that adopt 10% of the information, which of those is better or worse than each other? That's a complex question. I think goes way beyond the scope of this particular class, right? But yeah, that would be interesting to think about and interesting to compare for sure. Yeah, very interesting. I'm very interested personally in how we can fight miseducation and misinformation. And so I think those kind of questions are very important to think about strategically from a scientific perspective. If we want to educate more people about the truths about the world, how do we best do that? I think that's a very interesting question to consider. Yeah. Okay, so at this point, we've talked a lot about how to design this model. And this afternoon, we're going to talk in more detail about how to actually build the model. I'm going to spend the rest of the time this morning for the next half hour kind of breaking down other ways you might think of these different aspects of the model, right? Like what are agents, what are properties, what are behaviors, right? And so I'm going to give you a framework to think about that. So now we have a concrete example to work from. And the next step, I'm going to give you a framework that's going to allow you to think about these questions in a bigger picture type of sense, right? So what makes up an ABM? Agents, environment, interaction. That's it, right? That's basically it. And so what I'm going to do is I'm going to take each of those and break them down a little bit more to think about the questions you might ask, right? So there are a set of basic agent properties that NetLogo gives you for free. And I would just want to talk about those real quick. Just so you're aware of them, right? So you can use them when thinking about your model. There is who, and who is an identity of the agent, right? So each agent, each turtle in the model, when it's created, gets a unique number. And that's just an identity of that number. Now, in general, it's discouraged to use that number to do anything in the model, right? Because it could, depending on how the agents are created and deleted and what types they are, you don't really know what those numbers are, right? But sometimes it can be useful if you're debugging to just look at one turtle with one number, and so it's important to know that exists, right? Agents can have different breeds, and this is something we haven't talked about before, but it's important to the idea of agent types, right? So when you're designing your model, what agents there are, right, in the model, one of the things you might want to decide is that there are different types. They could have influentials and imitators, for instance, right? So I can assign breeds to my agents, and I could call one class of agents influentials and one class of agents imitators, and then I can say, rather than ask turtles, which asks all the agents to do, I can say ask influentials, and that will only ask the influentials to do something, right? And so this is an important notion within agent-based modeling, that we not only have a general class of all agents doing something, but we can then ask specific groups of agents to do something as well, right? We have headings, we have X coordinates and Y coordinates, we have shapes, we've seen all that. We also have labels and label colors, which is important for visualization if you want to, or debugging, right? So let's say I want to know what an agent's coefficient of imitation is, right? I can have that just displayed on the visualization, so then I can see to make sure it's correct, right? We can make the agent hidden. If you want to just not have the agent show up at all in the display, you can set the hidden to true, and it just won't visualize, right? So that's sometimes useful if you have agents who are not physically present in the model, but have an effect on the model in some way, right? The agents have a size, and then they have a pen size, and they have the pen mode, and that's up or down, right? And that just depends upon how they draw, right? So those are the basic agent properties. Any questions about those? Those are the properties that NetLogo kind of gives you for free. What is that? Yeah, so the proto-agents will get all these properties too as well, and you might make them hidden, right, or something like that. Is that what you're asking? Yeah, they may be the hidden ones. Yeah. A lot of times they probably will. So besides the NetLogo properties, agent or model properties, right, there's author-defined properties. These are properties that you as the model author can give to NetLogo. And you've already seen this a couple of times when they do the turtle zone, right? That's essentially doing author-defined properties. So in the traffic basic model, for instance, every car has a speed limit, a speed, and a speed minimum, right? And that's how fast they can possibly go, what their current speed is, and what the slowest they can go in. Now, what's interesting is you can set those properties three different basic ways. You can have them fixed values. So every agent has the value of 10 for the speed limit, maybe, right? You can have a distribution. Every agent chooses from a distribution. So, for instance, when we're talking about having a variety of coefficient of imitations, right, we can draw from a distribution of the coefficients, right? Or they could be variables or parameters of the system, right? So we could have a slider that controls that. And to get more complex, we can combine these, right? We can have a slider that controls the distribution that the agents then draw from, right? So we can combine these in different interesting ways. I'm just trying to iterate through all the possible ways you could build these different types of agents right now. Agent actions. So there's standard actions that the agents have, forward, right, left. There's one called hatch we haven't talked about, but hatch essentially creates a new agent that has the exact same properties as the current agent. So if you want to copy an agent, this is the way you do it. You do it called hatch. It's called hatch because turtles lay eggs, so that's the reason why it's called hatch, right? You can think of it as clone if you want instead, right? Die, move to, we've talked about all these different actions that they can take. But then you've already seen this. We can define actions for the agents. So transact in the simple wealth model was an action that we defined for the agents. It wasn't an action. Act cowardly was an action we defined for the agents, right? In the traffic basic model, there are two actions: speed up and slow down, and that's it, right? Now let's get into, this is something I've kind of alluded to, but we haven't discussed about. Besides having individual agents and having them take individual actions and having individual properties, we can have collections of agents and have collections of agents that do things together. And there are a number of different ways to create collection of agents. NetLogo provides you with a bunch of basic built-in collections. So there are patches, there are turtles and there are links, for instance, right? And we've already seen ask turtles, ask patches, ask turtles, ask links. But there's also a couple others we haven't talked about. You can ask turtles here. And turtles here is a collection that every patch has that defines all the turtles that are sitting on that patch, right? So I can ask all the patches to have the turtles here do something, right? There's in-link neighbors. So link neighbors or in-link neighbors is the set of all agents who are connected to me by a directed link that points at me, right? It's the set of all those neighbors on the edges of those links, right? So I can use that if I want to find out, for instance, in diffusion of information, if I want to find out what neighbors affect me, I can ask all in-link neighbors to do something, right? We have agent breeds that are collections, right? Influentials and imitators. And by the way, much like turtles own can create values, I can have influentials own and imitators own, which will then have properties that are specific to those agent types, right? And then I can do what are called agent sets, and these are ad hoc collections. So for instance, I can do turtles with wealth greater than 0, which we saw before, right? And that will be in the set of all the turtles who have a wealth greater than 0. I can do turtles on patches with x coordinate greater than 0. And it will give me all the turtles that are on a patch with an x coordinate greater than 0, right? And so these are different ways that we can get agent sets. Now, once we have an agent set, a lot of times we're going to ask it to do something. That's the standard thing. But sometimes we're going to create links to it, right? Or we might do other things along those lines. So we haven't talked about this too much in this class, but there is, besides agent sets, another way to represent a collection of groups of things is a list. We can just have a list of agents, right? Now, an agent set is actually, in an agent set, we actually know that each of the objects in that set is an agent. In a list, we don't know, but we might just have a list of the agent ID numbers, the who numbers, right? And so there's this list can hold any type of item, but agent sets can only hold agents. So for instance, the set of no turtles, right, is an agent set that has nothing in it, right, whatsoever, right? It's a special agent set. It's the null agent set. But a list would just be an empty list, right? And we can convert from the one to the other, and this code is actually slightly incorrect. I actually just realized that as I'm flipping through this, because they've updated it in NetLogo 6 now. So you don't do this way anymore. So I'll modify the slide and add it to it. But essentially, you could iterate through a list, and you could ask each element of the list to do something. You now have to use an arrow operator to get the question mark. You don't use the question mark anymore. So I'll have to update that piece of code. But essentially, that would be one way to do it. So rather than asking in a normal agent set, I would take the agent set and do something with it. If I have a list of agents, I have to iterate through the list and ask each individual agent to do something. This is kind of a little confusing at this point because we haven't done too much that's gone back and forth between lists and agent sets. But there are certain procedures that will generate lists and certain procedures that will generate agent sets. And so you need to kind of understand that there is a way to go back and forth. Yeah. Yeah. So you can create a list. There. I wish I had a good example. I think I have one in the chart. Let me see if I can find one real quick. I think I know where the one is. Yeah, discard that one. This one. Yeah, hold on one second. I think I've got it here. I'm not pulling it up right away. I'll come back to that this afternoon. We'll take a cleaner example of how to do that. But the point I want you to take away from this is that sometimes we have to convert between these agent sets and these lists in interesting ways. But we can talk about that more this afternoon. It's not terribly appointment for the theory, right? Yeah. Yeah. So exactly right. So the main difference is that a set can only contain unique items, right? And a list can have multiple items in it. But the other difference is that in an agent set, the NetLogo code knows that every element in that set is an agent, and so it treats it as a first-class object, right? I can now ask the things to do that. I can assume that it's going to iterate over that agent set, right? So I can, rather than, in this case, I have to say for each agent in the list, ask it to do something specifically. I could have just, if this is an agent set, I could just say ask a list, right? And it would execute the code on all of them individually, right? But yes, you can also have duplicate elements of the list, and so other things make it a little bit different from each one. I'll come up with a great example of how you need to do that this afternoon. It's important to realize, right, one small comment I want to make, right, this is big, and the only reason why I'm making this is because people tend to write bad ABM code at times, and they think it runs really slow, and they can't figure out why it's running really slow. And it's because they haven't thought about the computational efficiency of agent sets, right? So one thing you need to worry about is the ordering of how you create the agent sets, and one thing you need to worry about is the efficiency of creating agent sets. So let me show you some examples of that one real quick. So let's see, clear. Chapter 5, right? Okay. So in this piece of code, right, I'm going to create a whole bunch of agents, right? And they have different sizes. And I ask them to go forward 10 steps right away, just to show where they are. And now I'm going to ask turtles with size less than 1, let the big turtle be one of the turtles with size greater than 1, then ask that big turtle to set its size to a size minus 0.5 and set its color to red, right? So essentially what I'm going to do is I'm going to try and have all of the small turtles choose a big turtle, and then those big turtles are going to decrease their size, right? And if that's the case, then really what we should do is we should see that all of the turtles that are red now have a size less than 1, right? So if we hit go, right? But what we see is that there are some big turtles, right, that don't have the size that change, right? So, for instance, some of these red turtles, because of the way we did this code, right, we first asked all the turtles with size less than 1 to execute, right? But because we created that list right at the beginning, right, we created that agent set right at the beginning, over time, there will be some of the other turtles that become less than 1, but they're not going to act, right? Because they weren't less than 1 when we started this loop. Does that make sense? And so as a result of that, right, we might think of this as that it's going to have all of the turtles with size less than 1 take this action, but in reality, some of them are going to become smaller as a result of this action, so they're not going to take this action, right? Does that make sense, right? So it's important to remember that when we do that ask turtles with up there, right, we're going to get different effects than otherwise, right? So let's put this specifically. So if instead we were to change this code, and have, let's see, how would we do this? We'd have set big turtles be turtles with size greater than 1.0, right? And then we say, let big turtle be one of big turtles. Now we're going to get a different, I need to do let instead of set. Now we're going to get slightly different results, right? Because now we're having it control all the turtles before it happens. So now we have a lot fewer turtles that become red, right? Because we're only choosing the ones that happen beforehand, right? And if we keep running the code, right, they all eventually become red. Whereas if we did it the way we had before, they do have all eventually become red, but it takes longer for it to happen, essentially, right? Because of the way we have it set. Yeah. Does that make sense? It's a little complicated notion, but it's important to remember that when you do the ask, right, it can affect, it creates that agent set at that time, iterates through all those agents, right, and then only really changes which agents are affected that if you do another ask, right? So if you're doing something that's going to modify agent properties over time, you might want to capture which those properties they were before you started running that loop, right? Because otherwise you're going to get different effects than if you didn't. Does that make sense at a high level? Okay, good. So yeah. So let creates a variable that doesn't exist. Set can only modify a variable that already exists, right? So let is basically the way you create local variables in NetLogo. Okay? So one of the things I want to talk about agent sets, right, is agent set efficiency. So in this code, I'm basically going to set up the world so all the patches are roughly half are red, half are green. In this code, I'm going to ask the patches with p color equals red to count the number of patches that they have with p color equals green, it's greater than 5. Then if they are, I'm going to have a random number, right? And I'm going to do the same thing with the green patches, right? In this way as before. Now Go2 is similar, except you'll notice that in this code, there's several times where I'm saying patches with color equals green, patches with color equals red, right? And so what happens is that every time I run that code, it costs a lot of computational effort to find all those. So in this code, I pre-computed which patches were red and which patches were green, and then I can look to see what happens, right? And so I can actually run this version, right? And I can run this version, and version 2 is faster than version 1. Now, it's not obvious, but there's a way to show that. So let me show you real quick. I always have to remember these commands. Timer, right? So reset timer, and then okay. So we can modify this code. We can just say reset timer at the beginning, and then show timer at the end. Reset timer. Actually, it's easier to do this. Let me not do it this way. It's easier to do it if I do it like 100 times, because otherwise it becomes hard. So I can write a little piece of code right here. Reset timer, repeat 100, go 1, timer, print timer. So I just run the model 100 times, and it takes me 3.49 seconds to do it that way. If I do it the other way, where I cache the values, it's a little bit slower. So I heard about this, actually. So it turns out they actually changed the way caching happens, so it's not as important anymore in NetLogo 6. Someone just reported this bug to me recently. So it used to be that the second version would be about twice as fast as the first version, but they actually do some things for you behind the scenes where it's not as important anymore. I still think it's important to kind of keep some of these things in mind, but let's look at the other two examples real quick. I hadn't actually tested that yet. So here's a good example of the coloring, the ordering thing that we talked about. In Go 3, we're going to ask patches with p color equals red to count if the patches with p color equals green is greater than 5, then set their color to green. So it's going to find all the patches and turn them green or red, right? So if I run Go 3, wait, hold on, setup. Go 3, right? I get this world in which the whole world is green, right? Now Go 4, and so what's interesting about that is that this code never executes, really, right? Because there's never any patches with p color equal to red. In Go 4, I'm going to cache them beforehand, right? And then run it. And so in Go 4, I have to run setup again. Go 4, I get a very different result, even though the code looks very similar. So this is, again, a case where ordering is very important, right? In the first case, I cached which patches were green and red and then modified them. In the other case, I modified them on the fly, right? So just a small note that as you're working through these things, if you run into problems where you see patterns like this and you're like, this isn't working the way I want it to, you might want to look to see when you're updating your different things. Oh, by the way, there is a piece of code in here I totally forgot about that runs the test. Let's see if that gives us any different. So test 1, 2. So this, I'm going to repeat it 200 times. Yeah, so, why is that one faster? Let's see. Repeat and go on. I don't know. Maybe because I forgot to set up the first time or something. But this is more what I was expecting, where the second piece of code, which is the 3.0609, it's like, see, but that time it's not faster. So I think they did do some work on optimizing the efficiency for you behind the scenes in NetLogo 6. I need to reach out to the coding team and check in on that. Okay. So that's just some quick notes on agent set efficiency and computation. Let's see if we need to talk about anything else here. So it's important. I do want to mention a couple other quick notions when you're talking about designing an agent-based model. It's important to think about designing the level of an agent, and that often means thinking about what phenomenon you're interested in, right? So here's two models of disease states, right? The one on the left is a cancer model, right? And it's a cellular level cancer model, right? They're interested in how white blood cells and interact with tumors in the body, right? And they explore the interaction with that. The one on the right is also a disease model. It's a model of AIDS spread, right? But it's done using human-level models. So why do you think that they chose cellular-level ones in one case and humans in another case? Any ideas? I mean, you could have done an AIDS model that was cellular level, right? Yeah.
The AIDS model was trying to model an epidemic of how fast disease is spread.
Mm-hmm.
The tumor model was just trying to see how tumors grow.
Yeah. So the question was terribly important, right? That's the thing I want to get back to. And that's the thing I think you need to think about whenever designing your model. And I think it's the thing people overlook, right? You can't just go out and design an agent-based model to design an agent-based model. You need a research question that's going to guide you, right? And that's going to help you answer all these questions along the way, right? So we already talked about proto-agents. One other thing I want to talk about is meta-agents. This is not something that people do a lot of, but it's kind of cool, right? You could have an agent that is composed of other agents. And there's actually a cool command in NetLogo called tie that basically will physically tie one agent to another agent. So if one agent moves, the other agent moves as well, right? And so it's kind of cool. It is one way you could start to think about meta agents, right? So in that logo, right, I can go to a new world. Right? I can create just 2 agents, forward 10, right? And I can ask one of turtles, tie one of other turtles. Tie. I gotta look up the exact format of this tie. Tie. Oh, I have to do the create link. Create link with one of other turtles, tie. Right? And now, if I ask turtle 0 to go forward 10, the other turtle goes with it, right? Everywhere I do. Not sure it's that useful, but it's kind of a cool idea, right? I would love to see someone actually build a model that had like 5 agents all tied together and they represented like an organization interacting with 5 other agents who are tied together. I've yet to see it happen too much, but just something that I wanted to point out, right? And so we do have this notion in agent-based modeling of meta agents that isn't used very often, but the basic idea is that each agent can be composed of many, many other agents. Yeah. Yeah. Yep, exactly. Each agent is tied to the other agent, so each agent can drags along the other agent no matter what. Yeah, that's an interesting question. I'm not sure what happens if you ask both of the agents to do something. So let's see. If we say ask turtles forward 1, do they both go? I think they did. I don't. Let me. How can I figure this out? Ask turtles. Set. No, I don't know. I don't know a good way to check this out. I'm trying to figure out how I can see that they both moved. I think they did both move because the way the turtle, it should do it that way at least, right? The way the ask command works is it just circles through each agent and asks them each to do each command. So it'll do the first agent, drag it a little bit, and then it'll do the second agent and drag it a little bit, right? So I believe what it'll do is they'll be moving forward 2 spots rather than 1. So that should, we know what we could do. We can ask turtle set heading 0, right? Oh, that's interesting. So it did do it. So it set one to heading 0, and then it set the other one to heading 0, and when it set the second one to heading 0, it wound up changing the heading of the first one, right? So it does do it in that way, right? And now, so if I ask turtles forward 1, if they only move once, it should just move straight up or straight to the right. But I think what you'll see is it'll move straight up and then straight to the right. Yep, and there it does. Right. Actually, we could make this even easier. Ask turtles, pen down. Yeah, see? So they do. Okay. Right. Yeah. Like if I do it like, I'm not sure I totally understand. So I do pen up, forward 1, pen down like that. Oh, I gotta spell pen down. Yeah, you see it only drew the one little bit after the other turtle had moved, right? So both of them got the pen down command. So the red turtle went first, right? Move forward 1. No, the red turtles went second. The blue turtle went first, move forward 1 straight up. Then both of them then just the purple turtle sent its pen down, right? The red turtle it moved the purple turtle, which caused it to draw a line, but the red turtle had set its pen down, and then it set its pen down. Cool little project. I hadn't thought about that. A cool little question. Is there another question? Yeah. You would have to define a new agent, right? But yeah, it could, right? So you could have an organization agent that is composed of a bunch of other agents, right? That are worker agents, right? And that organization agent could have its own properties, like a physical location or something like that. Yeah, I could see it happening. It gets tricky. Like I said, not a lot of people actually do this. There's been a lot of theories about how cool it would be to do it, but people don't do it very often. Yeah, yep. Exactly, right, yeah. Yeah. I mean, I think you'd have to think about when that would be useful and when it wouldn't be, right? It might be useful to just make each agent have a property that is a membership in the household or something like that, but yeah, it's a cool idea. Any other questions? Okay, well, we're actually just about out of time. So I think it's a good breaking point, because at this point, what I'm going to talk about next is kind of some of the more detailed aspects of agents and environments, and we can save that for Monday, and we'll come back for the tutorial in the afternoon. Does that sound good there for everybody? Okay, cool. Okay. Take a break for lunch then.